I am still Pierre Becquerel, and I will talk to you about message recovery fault laser injection attack on the McAleese crypto system. It's a joint work I've done with Brice Colombier, Vlad Dragoy, Alexandre Menu, and Lilian Bossuet. So the goal of our work is to cryptanalyze one of the 4 finalists of round 3 of the NIST competition, and the candidate's name is Classic McAleese. And to do this cryptanalysis, we will use 2 tools. First of all, we will do laser fault injection, and then we will use integral linear programming to recover the message. So Classic McAleese is based on the Niderator crypto system, and we will only focus on the encryption part. So the encryption part works as follows. You have the message, the public key H pub, which is a binary matrix of size n-k times n. And the encryption process has 2 steps. First of all, you encode the message gem into an error vector E of length n and weight t. And then you just have to sum several columns of H. When I say sum, it's an XOR of T columns of the matrix public H to obtain the ciphertext S. So the security of this problem is based on the syndrome decoding problem. So the problem which is used in practice is a binary syndrome decoding problem. You have a binary matrix H, which coefficients are in F2 of size n-k times n. You have a vector S of n-k coordinates and an integer T, which is the weight of the error. And the problem is to find a vector X of weight T, such that the product H times X is equal to S. So this is an NP-hard problem. So it's not the problem we will try to attack. We will try to attack something slightly different. We will try to attack a problem where you have the entries in N. So you have integer entries, and we will search for a vector X of weight T, such that H times X is equal to S. But all the values are in N now. So how can we go to one problem to another? The idea is to use laser fault injection. So laser fault injection, they were proposed in 2002 by Skorobogator, and the principle is to shine an infrared laser on the backside of an integrated circuit. So you have the circuits, you have the laser, and you will act on the circuit with infrared lasers. So how does it work? So what we can do, we can corrupt instructions. So you have the operation code of the instructions, which are encoded in binary. And when the information move from the flash memory to the computers, to the processor, we can flip a bit. We can do a bit set. So if you have a look at the XOR instruction, which is here, you have a list of 1 and 0s, and the laser can flip a bit to modify this 1 to become a 0. Can modify the 0 to become a 1. That's what we can do. We can do a bit set using our laser. So if we do so, the XOR become an addition, and we can turn addition, which are into F2 in the classic scheme, into addition over N. That's the first main idea. So we have done several experimental results, and we noticed that we don't need all the coordinates of the faulty syndrome to be in N, but only a fraction of those coordinates are needed in order to solve the problem. For instance, for the parameters used in classic McAleese, we only need around 40% of the faulty syndrome entries. It's enough to solve the problem. So we realized this solution, and we did it on a desktop computer. For the classic McAleese with 128-bit security, we needed less than 1 second to recover the original message. And for higher security levels, we need less than 3 seconds. Thank you very much for your attention. I think I am just 5 minutes.
Thanks for the talk. Any question?
Oh, okay.
Countermeasures.
So for the laser fault injection, the basic countermeasures are hardware countermeasures in which you cannot have access directly to the components. You see, the laser is acting directly on the integrated circuit because we have directly access to this part. You can do devices such that you cannot unsecure this part of the components. Just add some devices, some hardware stuff. That's a basic countermeasure used against fault injection attacks.
We have time for another question. Then let's thank the speaker again. Okay. The next talk is multi-source non-malleable extractors and application. The talk is going to be given online by Shenzi Zhu. Shenzi, can you hear us? Are you there?
Yeah, hello. Yeah.
I guess.
Let's share screens now.
Can you share your screen? I need to stop.
yeah.
Share. Amit.
Can you see my screen?
I cannot do it. What is it? Okay.
Yes, we can.
Okay. Okay, so yeah, hello everyone, I'm Chen Zhi. Today I will introduce our work on the multi-source non-malleable extractors and its application. So it's a joint work with Skorobogator and Algerian Sunni Masen. Yeah, so I will start by introducing what is a two-source non-malleable extractor. So this notion is introduced by Cheragachi and Griswami in 2014. So in this setting, we start with two independent weak random sources. So here the weak means that the sources are not uniformly random. And we want to use the extractor to extract n-bit strings that are close to uniform. And in the setting of non-malleability, we assume that each source can be tempered independently by arbitrary functions. And the security requires that the temporal output is either the same as the original output or it is independent, which means the value is destroyed. And the randomness of a source X is measured by its mean entropy. So if the mean entropy of a source is greater than K, it means that for any X, the probability that this source is equal to that X is less than 2 to the minus K. And in this setting, we assume that both X1 and X2 are n-bit sources with mean entropy K. We also call such sources as the NK sources. And formally, the non-malleability is defined as the joint distribution of the original output and the temporal output is epsilon close to the joint distribution of the two n-bit string, where the first n-bit string is uniformly random, and the second n-bit string is either the same as the first or it is independent. And here the epsilon is called the error of the scheme. So in this work, we introduce a new notion called the multi-source non-malleable extractors, which is a generalization of the two-source one. So instead of the two source, now we have S independent NK sources. And the non-malleability can be naturally extended to the following. So we consider that each source is also tempered independently by arbitrary functions, and we can define the security in a similar way. But however, this definition is actually weaker than the two-source one, because you can build such a thing by simply apply the two-source non-malleable extractors to X1 and X2 and ignoring the rest of the source. And however, there's no prior results that consider the non-malleable extractors beyond the independent tempering. So in this work, we ask the following questions. So can we protect against the tempering functions that temper multiple sources together? And what is the mean entropy is required for each source, and what is the error? So the most general model one could consider here is the overlapping joint tempering, so which means that for each I, its temper function can depend on a set of input sources Ti. And this Ti can be different for each source, and it can be arbitrarily chosen. We mentioned that this model is also previously proposed by Goyo and Kumar in 2018, but they are working in the context of non-malleable secret sharing. And however, we find it's hard to protect against this general overlapping joint tempering. So instead, in this work, we considered what we call the cover-free tempering, which is a overlapping joint tempering, but with some constraints. So given overlapping joint tempering, we said it's I cover-free if there exists an xj, so that no tempering set tk containing both xi and xj. For example, here, you can see for I equal to 1, the x1 and x4 does not contain in any tempering set tk. And we say it is cover-free tempering if it is I cover-free for each I. We'll see that this tempering model actually includes a rich class of tempering functions. So for example, this cover-free contains independent tampering. It can also contain destroying tampering, which means that in destroying tampering, so it means that the input sources can be divided into at least 2 destroying sets, and the source in each set are tempered together. So for example, there was cover-free tampering because for each xi, you can find another xj and another tempering set. And then because they're destroying, you can they're not containing any tempering set together. And moreover, this cover-free tampering is strictly richer than a destroying tampering, as it contains some like fancy tampering functions as the following. For example, we call the circles of size 2 for at least 4 independent sources. So so the tempering is like the following. So each xi, the tempering of each xi depends on both xi and xi plus 1. You can see this tempering function are not destroying tempering because you cannot divide the source into 2 destroying sets. But however, it is cover-free because for each xi, both xi and xi plus 2 are not containing any tempering set together. And now I'll briefly summarize our contributions. So first, we introduce a notion of the non-malleable, a multi-source non-malleable extractor. And then we give an efficient construction of these at-source non-malleable extractors against the cover-free tampering. With the main attribute requirement is linear in N, and with negligible error and polynomial outputlets. We also show that our construction satisfies a property called efficiently pre-image sampleable, which means that given any output, one can efficiently do a sampling over its pre-image. Using those techniques, we also show that we can resolve some open problems in the areas of non-malleable secret sharings and network extractors. Yeah, that's the end of my talk. Thank you for your attention.
Questions? No, well, I think we can go with the next talk. Thanks. Let's thanks again the speaker. Yeah. So the next talk is black box non-interactive non-malleable commitment. Rashid is going to give the talk.
Hi, can you see the slides?
Yes, we can.
Okay. Hi, everyone. I'm Rachit, and I'm excited to discuss with you about our work, black box non-interactive non-malleable commitments. This is joint work with Dakshita Khurana, George Liu, and Brent Waters. Let's begin with our result. We construct non-interactive non-malleable commitments. What are commitments? Commitments are a two-phase protocol where there's a commit phase and then there's an opening phase. In the commit phase, Alice, let's say, commits the message M to Bob. And in the opening phase, Alice opens the message that she initially committed to Bob. And what I mean by non-interactivity here is that both these phases happen as single message protocol. So there's no common random string, there's no setup, and these are just single message interaction from Alice to Bob. And additionally, we construct non-malleable commitments. So what is the notion of non-malleability? Non-malleability means that a new party, let's say Mallory, if it enters the system, and if it tries to tamper the system or look at the interaction and change the interaction in any way, she should still not be able to learn any relevant information about the system. So how are these built in practice? In the non-interactive setting, we first build them for a very small number of tags. By tags, I mean very small number of parties. Let's say log, lambda, many parties. And this is not really relevant in practice because it's a very small set. And then after we've built such a set for these number of parties, we amplify it to let's say, constant number of parties or exponentially many parties. So there's a tag amplification procedure that happens in literature. And the way we do it is we require the use of NIVIs to do this. NIVIs are non-interactive witness indistinguishability proofs. And using NIVIs means we make non-black box use of the underlying cryptography. So our result, we remove the use of NIVIs, simplify some assumptions, and make black box use of cryptography. There's an additional caveat in our construction where we go from non-uniform secure log lambda many parties to uniformly secure exponentially many parties. And I'll talk about this caveat and some techniques towards the end of the talk. So let's look at some prior work. We started in 1991 with a logarithmic round construction from one-way function. And since then, there has been constant research in the field to improve this round complexity and simplify the assumptions that we get non-malleable commitments from. So there are 3-round protocols, 2-round protocols, and in the end, we have interactive protocols, non-interactive protocols from different assumptions. And the focus of our work is only on this non-interactive setting. So let's look at this tag amplification procedure, which I was talking about. So the way we do tag amplification is, let's say we are at log lambda many parties. We go to log lambda many parties, then lambda many parties, and 2 to the power lambda many parties. So we define an exponential amplification algorithm, and then we do it recursively a few times, a constant number of times. And all the prior works in non-interactive, non-malleable commitments use sub-exponential NIVIs to construct this. And you only know NIVIs from, let's say, bilinear maps or de-randomization assumption and some trapdoor permutations. So the goal of cryptography is to get more simplified assumptions and increase the realm of assumptions that we know this tag amplification procedure from. And that is precisely what we do. So what are the ingredients that we use since we remove NIVIs? We use something called as hinting PRGs, which were introduced by Coppola and Waters in 2019. Hinting PRGs are a special kind of PRGs. So PRGs are length expanding functions where the goal is to output a length expanding function such that the output is computationally indistinguishable from random. But in hinting PRGs, you give certain additional hints about the seed, and you can still argue computational indistinguishability. The important part is that we can show how to build hinting PRGs from computational Diffie-Hellman or learning with errors. And the second component of our tag amplification procedure is going to be keyless collision resistant hash functions. So keyless collision resistant hash functions require no setup, and they satisfy the collision resistance property, which means that if given 2 values, it's hard to find a collision. And a common example for such a hash function could be SHA-256. So again, we construct non-interactive, non-malleable commitments. But let's talk about the caveat in our construction. So as I explained, we go from log lambda to 2 to the power lambda, and we apply our amplification procedure many times. But note that if you go from non-uniform security to uniform security, you cannot really do this even 2 times. Like after the first transformation, you get a uniformly secure log lambda scheme. So you cannot really do this generically. So in our paper, we actually introduced a new notion, which we describe as it's stronger than uniform security, but weaker than non-uniform security. So let me talk about this. What is uniform security? We define a security definition between a challenger and an adversary, where the adversary is probabilistic polynomial time. And for non-uniform security, we say that the adversary gets some access to some advice string. So we define a notion of where instead of the advice string, we give the adversary access to some program. And using this program, it can ask the challenger to run in some 2 to the power lambda to the power e time, where you can imagine that e is greater than 1. So the adversary is getting exponential time to run this program. And the output is returned to the adversary. And the goal of this experiment is to still argue that PPT adversaries will not be able to win this game with more than negligible probability. So this notion we call as e-computationally enabled. So I want to end with some questions. So one basic question that you can ask is, since you go from non-uniform to sort of uniform, or like this notion of e-computationally enabled, in an ideal case scenario, you would like to go from non-uniform security to non-uniform security. And we actually have a follow-up work, which requires some new techniques. The second question that I want to pose is, so our technique is basically, if you're aware of the Coppola-Waters 2019 construction, it's adapted into this commitment setting with some removing some setup and doing some additional generalization. So can we even generalize it more and sort of use this framework of using hinting PRGs to prove consistency or CCS style security checks? And the third would be, after the result of Coppola-Waters in 2019, they were able to remove hinting PRGs and get it from something simpler, which was injective trapdoor functions in the context of public key encryption. So can we do something simpler in the context of commitments as well? So thank you.
Are there any questions? Okay, we have a lot of time. I have a question. So one of the assumptions you have is a keyless collision resistant hash function. And I guess by assuming that, that's why the adversary at the end has to be uniform, right? Yeah. Is that the only reason why you need a uniform adversary, or are there other reasons?
That's pretty much the only reason. And basically in our new work, so there is this notion of non-uniform secure keyless collision resistant hash function, where collision resistant hash function are by definition like a very uniform primitive, because you can, for a non-uniform adversaries, you can have the collision hardwired, right? So there are this new kind of hash functions by Bitansky, Kalai, and Panev, which say that given some state S information, you cannot have like S square many collisions. So using this, you can sort of hope to get maybe non-uniform security, but it's a little bit more trickier, and we have a follow-up work. But that's the only reason, you're right.
Okay, thanks.
Yeah. Thank you.
Any other question? Check. Okay. Let's move on with the next talk. So the next talk will be non-interactive. The next talks will be non-interactive distributional indistinguishability and non-malleable commitments. The talk is going to be given online by Dakshita. Are you there?
Hi, yes, I'm here. Let me make sure I can share my screen.
Okay, perfect. I'm going to mute the audience. You can start whenever you want.
Thanks. Do you still see my slides on the whole screen?
Yes.
Okay, great. Thank you. Okay, so this talk is going to be about non-interactive distributional indistinguishability and an application of this notion to non-malleable commitments. This is a new notion we introduced. So let me motivate the setting with the following question. Can we achieve privacy-preserving arguments that...
Can you stop for a second?
Yes.
Sorry. So... okay. What about now? Thanks. Okay, you can start again from the beginning.
Okay, thanks. All right, so yes, so this talk is about non-interactive distributional indistinguishability and non-malleable commitments. And the motivation for this problem is the following question. Can we achieve privacy-preserving arguments that do not require interaction? And while this is known to be doable either in idealized models like the random oracle model, or by assuming some form of trusted setup like a common reference or a common random string, the goal of this work is to understand whether we can achieve new types of privacy-preserving arguments in the plain model that do not require access to trusted setup or a CRS. And Let me briefly go over prior work in this specific setting. There's, of course, a lot of wonderful literature on building privacy-preserving arguments, like I said, in the random oracle model or with the CRS, and please refer to the full version of my talk or my paper for more details on that. Because I don't have time here, I'm going to focus on the plain model. And there we know that non-interactive witness indistinguishable arguments exist from de-randomization assumptions or bilinear maps or indistinguishability obfuscation. There's also a notion called witness hiding that we believe exists, and a recent work of Quick and Dahl and Zandri showed some universal constructions and some constructions under new assumptions on non-existence of witness encryption schemes. Nevertheless, despite knowing these two types of non-interactive arguments in the plain model, without CRS, there are still major gaps in our understanding of what can we achieve non-interactively. And let me try to illustrate one of these gaps with the help of an example. So suppose there is a cryptocurrency that allows for finalizing transactions while keeping the amount being transferred hidden. Now, in general, hiding things could lead to unwanted behavior, like someone transferring more money than they actually have in their account. And in fact, existing currencies like Zcash deal with these problems by using some form of zero-knowledge proofs, non-interactive zero-knowledge proofs in the CRS model to prove the correctness of encrypted transactions. But the CRS turns out to be quite expensive to generate because it needs to be generated by a trusted party. So the question is it possible to achieve this type of functionality in the plain model? And as a simplification, can a prover encrypt a message and then prove that the message is smaller than a given value, let's say 10, but without revealing the message itself? So in a non-interactive commit and prove argument, a prover with input a secret message M and a public predicate phi wants to generate a commitment to M and additionally prove that the committed message satisfies this predicate phi, while guaranteeing soundness and privacy. So the soundness guarantee is that if the verifier accepts the prover's proof, then the commitment C is indeed a commitment to a message M that satisfies the predicate phi. The privacy guarantee is that the commitment and proof together should not reveal the message M. And what this means is that for every predicate and every pair of messages, M1 and M2, that satisfy phi, the output of the prover given the first message should be indistinguishable from the output of the prover given the second message. And now, while this seems like a very fundamental problem, unfortunately, existing non-interactive proof systems like NIVIs and witness hiding do not suffice to solve this problem, just because the privacy guarantees they provide are somewhat orthogonal to what is needed here. So in this work, we take some of the first steps towards rectifying this situation and building non-interactive proof systems in the plain model without setup that provide these types of privacy guarantees. And in particular, we introduce a new tool called a NIDI, a non-interactive distributionally indistinguishable proof. And we construct it based on indistinguishability obfuscation and variants of one-way functions. And we use it to obtain non-interactive commit and prove, as well as non-interactive, non-malleable commitments. We show that these resulting applications are, in some sense, non-interactive. So what do I mean by that? The interaction pattern of the resulting commit and prove argument is as follows. The prover on input a message M and predicate phi is actually going to be generating a sampler and sending the sampler to the verifier. The verifier will run a local randomized algorithm on this sampler, and the result of that algorithm will be a commitment string C. We'll have the usual completeness property in that the string C is going to be a commitment to the message M that the prover intended to commit to, as long as both of them are honest. The soundness guarantee will be that if the commitment string is not bottom, then it is actually a commitment to some message that satisfies this public predicate phi. And the privacy guarantee, like before, is that for every pair of messages that satisfy the predicate, a sampler that's generating commitments to M1 is going to be indistinguishable from a sampler that's generating commitments to the other message M2. Now, the technique that we use to build such a commit and proof can actually be abstracted out into this more general tool, which has, again, the following syntax. The prover on input a language L and a distribution D that samples instance witness pairs in the relation of the language is able to compute a sampler and send it to the verifier. And given this sampler, the verifier can interact with it and obtain samples from the language. So samples of instances in the language. And so the completeness guarantee is usual. The soundness guarantee is that if the sample that the verifier obtained was not bought, then it must be an instance in the language. And the privacy guarantee is that for all pairs of distributions that sample pairs of indistinguishable instances, a sampler that outputs samples from the first distribution is going to be indistinguishable from a sampler that outputs instances from the second distribution. So the point is, if the x's sampled by these two distributions, D1 and D2, are indistinguishable, then the samplers will produce outputs that are indistinguishable along with proofs. So there is this additional soundness guarantee that this adds to this setting. And now we, as Rachit already described, existing non-interactive schemes and existing non-interactive CCA commitment schemes have an important tag amplification component that requires commit and proof. And we show that this can actually be achieved in the plain model via a NIDI. So a NIDI is sufficient for this specific application to tag amplification for CCA commitments. And so let me just summarize quickly. We introduced this new tool. It roughly guarantees that when two statements are indistinguishable, then so are the statement and proof combinations. It has applications to commit and prove and to CCA commitments, and we believe this may find additional applications. Because I didn't have a lot of time, I couldn't go into many of the details, but the paper is on ePrint if you want to take a look. Thank you.
Is there any question? Okay.
Thanks for your great presentation. So do I get correctly that you have just one shot, or you assume that there is offline something to share with prover, let's say committer and verifier?
So it is not completely one shot in the sense that the verifier obtains this commitment string, which is like different for different inputs of the verifier. So the prover, once it sends this sampler, does not know what sample the verifier ended up with. Depending on application, they may or may not need to know what it is. So there's a bunch of applications where like this may not be necessary, and a bunch of applications where this could be. And like in the paper, we describe like what the implications of this are in a little more detail.
So we couldn't use subversion resistant, let's say simulation extractable or simulation sound NISCs that they are to run. Verifier sends some CRS and prover uses them, and you guarantee that the proof is non-malleable. So
right.
like, could we use them or? So
here, one of the goals is to just not rely on any CRS at all, because and having the verifier send the CRS first would, again, like you said, would be actually be two messages, whereas this can be like a single shot in certain settings, and maybe some other settings require the prover to know what output the verifier obtained. And in those settings, this needs like first message from the prover, response from the verifier. So this is like completely non-interactive in some applications and needs this extra message in some others.
Okay.
Any other question? I might have a question. So you introduced this new notion. It's very powerful, this non-interactive distributional indistinguishability. You show that IO plus something else imply needy. What about the other direction? Could you show needy, or have you thought if needy imply some weaker form of IO?
That's a great question. It's a great question. I haven't thought too hard about it. I have tried to simplify, like reduce the assumptions, try to get it just from LWE, not been very successful in doing that so far. But I haven't tried hard to prove that NIDI would imply IO. So great question. I don't know, unfortunately.
Okay, thanks. Any other question? I guess no. So with this, we conclude the sessions. Let's thanks all the speakers again.
You're muted.
Okay, so thank you everyone for listening. This was the last session of the last day, which means the conference is officially over. There is one more thing, couple. Some of you, if you want, you can return the badges, you get a gift. Some of you enrolled for the guided tour, so that will start in 30 minutes, something like that. That being said, let me also share a slide. Where is the slide? The slide was here. Here. Zoom. Share screen. Yeah. Hopefully you can see it. So it's just a slide for Eurocrypt next year, so Eurocrypt 2022. It will be happening from May 30 to June 3 in Trondheim, Norway. So yeah, start already thinking how do you plan to go there and enjoy also nice time there. That being said, I do hope you enjoyed in Zagreb. Maybe those that are vegetarians you enjoyed a little bit less. But others, hopefully you had a good time, and hopefully we see each other, well, sooner than we had now 2 years of break. Thank you all.